Right now I'm going to give you the three kinematic equations. These are not going away. They'll keep popping up all year. I'm going to give you the three of them, and then I'm going to take the time to derive them. You do not need to know the derivation, but know that it is completely fair game for me to put that as a bonus question on a test for you to be able to derive the three kinematic equations. So, the numbers don't matter, so I'm not even going to bother numbering them. The order that I give you these don't matter, but here they are. Your first kinematic equation, V final equals V initial plus AT, where V final is the final velocity or speed, depending on the problem, so it doesn't matter if it's velocity or speed. This would be your initial velocity. A is acceleration. And t is time. Now, this equation you've already seen, it's just rearranged. Acceleration equals change in velocity over time, which equals v final minus v initial over time. Again, this equation is just this equation rearranged. So this, if you know the definition of an acceleration, you can get that first equation. Okay, here is our second equation. Delta x equals 1/2 a delta t squared plus v initial delta t. Delta x is displacement. A is acceleration. These delta t's are any time interval. Remember, delta is just final minus initial, and vi is your initial velocity or speed if you're not taking direction into account. This equation can really mess you up if you're using the wrong sign, so pay attention to your displacement and your initial velocity. If they're negative, it matters. If the acceleration is negative, it matters. You can't just take those away. And then our third equation I like to call the no time equation. V final squared equals V initial squared plus 2a delta x, where Vf is your final velocity, Vi is the initial velocity, A is acceleration, and delta x is your displacement. And why is it called the no time equation? Because you'll notice that there is no time in it. So you can use this equation if you're not given time. I find this is actually one that is most often forgotten about, but it's pretty easy to use. The biggest mistake I see when using this equation, and again, I recommend using it, is forgetting to square one or both of these. So this is your no time equation. If you don't care about how these were derived, then you can stop watching now. If you do want to see the derivation, at least for the second and third one, the first one I just showed you, then I will keep on going and you can keep on watching. Now we're going to get to the fun part of deriving all of these if you chose to keep on watching. Again, these are very fair bonus questions for a test, so it might be in your best interest to keep on watching if you're interested in a bonus. The first equation really doesn't need any derivation, so V final equals V initial plus AT. That was just, again, acceleration equals delta V over T, which equals V final minus V initial over T rearranged. So there's nothing to derive for the first equation. Our second equation, delta x equals 1/2 at squared plus v initial delta t. Let's start with a velocity time graph. And when we did the lab, the first lab that you had to write the lab report on, you got velocity time graphs that should have looked something like this. I'm drawing a dotted line because we're not going to keep it, where the y-intercept was 0. What we're going to do is focus on a velocity time graph. So let's get rid of that y-intercept and those lines, where you have a non-zero y-intercept. So let's just say that this is any arbitrary initial velocity, and my ending point on the line is any arbitrary final velocity. And this right here would be my final time, and starting over here would be my initial time. You should very easily be able to tell me now how to get displacement from a velocity time graph. And displacement is just area. So if we're looking for the displacement from the velocity time graph of this shape, we're going to want to break it into a triangle and a rectangle. And we'll call the triangle 1 and the rectangle 2. And what we're going to do is take the area of both of these. Again, because area gives you displacement. So starting with the area of 1, which is the triangle. Area of a triangle equals 1/2 base times height. So this will be 1/2 times the base of my triangle, t final minus t initial, times the height of my triangle, v final minus v initial. So this equals 1/2 delta t delta v. Delta, again, just final minus initial. We know that acceleration equals delta v over delta t. So therefore, acceleration times delta t equals delta v. I'm going to substitute this in for delta v, leaving me with 1/2 delta t times a delta t. Multiplying that out, we get 1/2 a delta t squared. And that's the area of the triangle. Next part is a little bit easier to take. We're getting the area of the rectangle. So the area for segment 2 is just equal to my base times the height. Base of the rectangle is t final minus t initial times the height, v initial. So this equals v initial delta t. Getting the total displacement, remember, displacement from a velocity time graph is area. So total displacement would equal delta x equals the area of 1 plus the area of 2. So this gives me 1/2 a delta t squared plus v initial delta t. And I'm out of room. I'm just going to write it nicer on the next. So from the graph, again, area of a velocity time graph gives you displacement. The displacement was equal to the area of the triangle, 1/2 a delta t squared plus the area of the rectangle, v initial delta t. And the reason I use the deltas here is because this can be for any time interval. So you'll see me switch whenever I do examples between using just t and delta t. Again, it doesn't really matter. The delta t is just letting you use this for any particular time interval. So that's how we derived the second kinematic equation, delta x equals 1/2 a delta t squared plus v initial delta t from the velocity time graph. The next derivation is for the no time equation. So this is going to be pretty algebra intensive. Just bear with me. We're going to start with the equation delta x equals 1/2 a delta t squared plus v initial delta t. Because this is called the no time equation, the first thing we want to do is get rid of time. Going back to my equation for acceleration, a equals delta v over delta t. If I rearrange this, delta t equals delta v over a. I'm going to substitute in this delta v over a for my t's, or delta t's. So this leaves me with delta x equals 1/2 a delta v over a squared plus v initial delta v over a. Now it's algebra. So delta v equals v final minus v initial. Let's break that apart. Delta x equals 1/2 a v final minus v initial over a squared plus v initial times v final minus v initial over a. Since fractions make things difficult, let's start getting rid of them. So I'm going to multiply everything on both sides by 2. So this gives me 2 delta x equals, this 2 goes away, a v final minus v initial over a squared plus 2 v initial v final minus v initial over a. So I'm going to now rewrite the right-hand side of the equation, factoring out the 1 over a's from both sides. So this equals a times 1 over a squared v final minus v initial squared plus 2 v initial times 1 over a v final minus v initial. Sorry for running out of room there. This a cancels out that, so we're left with 2 delta x equals 1 over a v final minus v initial squared plus 2 v initial 1 over a times v final minus v initial. Again, I don't like fractions, so let's get rid of the 1 over a by multiplying both sides of the equation by a. So now we get 2a delta x on the left equaling, the a's cancel, v final minus v initial squared plus 2 v initial v final minus v initial. No fractions is going to be a lot easier to work with now. 2a delta x equals, I'm going to FOIL v final minus v initial squared. So this would be v final squared minus 2 v final v initial plus v initial squared. So that was just FOILing v final minus v initial squared plus 2 v initial v final minus 2 v initial squared. Minus 2 v final v initial plus 2 v final v initial cancel out. This leaves us with 2a delta x equals v final squared plus v initial squared minus 2 v initial squared. Plus v initial squared minus 2v initial squared is minus v initial squared. So 2a delta x equals v final squared minus v initial squared. And if I bring the v initial over to the other side and just flip these, we end up with the no time equation, v final squared equals v initial squared plus 2a delta x. So after a whole bunch of really fun algebra, I find this fun, we end up with the no time equation. Again, I don't expect you to know how to do this, but it is fair game if I were to put a bonus question on a test to derive one of these two equations.